Good morning to one and all. In today's lecture, we'll discuss about the narrowband noise. Basically, the narrowband noise is similar as low-pass filtered noise, where here at the receiver side, the ideal low-pass filter is considered as your narrowband filter. So at the input, we have a power spectral density of the Gaussian white noise that is denoted by WT. So the power spectral density that is denoted by SWF is equals to N naught by 2. Now it is passed through a narrowband filter, that is the signal processing state where the band limited is B hertz. So when it will pass through the narrowband filter, at the receiver side we'll get NT, that is your narrowband noise. So we can see the practically the narrowband noise spectrum is, so it is practically we can represent it as like this. So we can see over here that the narrowband noise spectrum is centered at the midband frequency, that is plus minus Fc, where the dotted line denotes your ideal curve. So we say it as power spectral density of narrowband noise, white noise, that is your frequency Fc. For the positive side it will be Fc minus B up to Fc plus B, and same we'll consider on the negative side. Now we note a point over here that the sample function of narrowband noise, that is denoted by small n-t of the narrowband, is similar to sine wave approximately, that is very slow in amplitude and phase. So we can see over here that your nt is represented over here. It represents in the waveform of sine wave. So it looks like an envelope of nt. Since the nt is narrowband noise, which is random in nature, so we called it as narrowband noise process, that is denoted by capital NT. Now here we see the narrowband noise process. Here the narrowband noise process, that is denoted by capital NT, consists of two components. First is your in-phase component, that is denoted by NIT cos 2 pi f ct, and the second one is your quadrature component. For this, we will see first the generation of narrowband noise, that is your capital NT. So it consists of two components. First is your in-phase component and the second one is your quadrature component. So in-phase component is denoted by NIT and your quadrature component is denoted by NQT. Now it is multiplied with, NIT is multiplied with cos 2 pi f ct, while your NQT, that is the quadrature component, it's multiplied with your sine 2 pi f ct. And here we had a summer, so we can see that your in-phase component is positive while your quadrature component has a negative sign. So we can denote it as your capital NT is equals to NIT cos 2 pi f ct minus NQT sine 2 pi f ct. So here NT represent mathematically in terms of in-phase and quadrature components having band limited of twice B, that is centered at frequency Fc. So we can say that both the terms are low pass random process. Now coming on to the extraction of in-phase and quadrature component. Here we have taken NT. Now your in-phase component is multiplied with 2 cos 2 pi f ct, while your quadrature component is multiplied with minus twice of sine 2 pi f ct. Now it is followed by a low pass filter. So at the output of the first we'll get, that is your NT twice cos 2 pi f ct. In place of NT we can put NIT cos 2 pi f ct minus NQT sine 2 pi f ct. So we can solve it as NIT is equals to twice of cos squared 2 pi f ct minus NQT into twice sine 2 pi f ct cos 2 pi f ct. Now using the formula we can see over here that your twice cos squared 2 pi f ct is 1 plus cos 4 pi f ct, while your twice 2 sine 2 pi f ct into cos 2 pi f ct is your sine 4 pi f ct. So here we get three terms over here. That is, first is your NIT plus your NIT cos 4 pi f ct minus NQT sine 4 pi f ct. So here we know we have a low pass filter over here. So it will discard all the high frequency component and it will remove the high frequency component. It will pass only low frequency component. So we will get only our NIT, that is your in phase low pass random process, and these are your high frequency components, so it will be removed by your low pass filter. Now second, we'll see for the quadrature one. First we have seen for the in phase, now we'll see for the quadrature one. Here it is passed to minus twice of sine 2 pi f ct. So we'll get over here nt into minus twice of sine 2 pi f ct. In place of nt we can put nit into cos 2 pi f ct minus nqt into sine 2 pi f ct into minus twice of sine 2 pi f ct. Now when we will solve it, we'll get minus nit into 2 sine 2 pi f ct into cos 2 pi f ct plus nqt into 2 sine square 2 pi f ct. So in place of 2 sine 2 pi f ct into cos 2 pi f ct, it will be sine 4 pi f ct, and your 2 sine square 2 pi f ct, it will be 1 minus cos 4 pi f ct. So we'll get three terms over here. The first one is your nit sine 4 pi f ct minus nqt into cos 4 pi f ct plus your nqt. We know we have a low pass filter, so it will remove the high frequency component, it will pass only the low frequency component, so we will get the output as nqt. So we can say that the quadrature low pass random process. Now coming on to the properties of narrowband noise process, that is NT. First property, if your NT, that is your narrowband noise, is Gaussian in nature, then your frequency components, that is your in phase and quadrature phase, it will be Gaussian in nature. Second property, if your NT is stationary, then your both the frequency components, that is your NIT in phase component and quadrature component, will be strictly stationary. Now the third property, when your NIT and NQT has mean 0 and power spectral density, that is SNIF, is equals to SNQF, that is both are identical, or we can say same, we get a relation of here of SNIF or SNQF. So it is SNF minus FC plus SNF plus FC, having the band limited minus B to B and 0 otherwise. So we'll see the relationship between your SNQ and SNIF and SNF. So here we have considered the Gaussian white noise, that is denoted by SWF. Now it is passed through a narrow band filter that has band limited bandwidth of B. So at the output we'll get narrow band noise having the power spectral density SNF. So here we can see we have power at origin, it will be N0 by 2. So your SNF will be at 0 origin, it will be N0 by 2. So here we'll see the area of the positive portion only. So we can say that integration minus infinity to infinity SNF df will be 2 N0 B. Since we know that the total, we'll see the area of the positive portion only, so it will be N0 by 2 into twice of B, so that is equals to N0 B. So considering total area of the curve, it will be twice of N0 B. Now according to the relation of power spectral density, SNIF is equals to SNQF, that is both are identical. So your SNF minus FC plus SNF plus FC having band limited minus B to B or 0 otherwise. Now here we will see that when your SNF minus FC can be obtained by shifting the spectrum towards right. So we'll see we will shift the spectrum towards right. So when we will shift it towards right, we'll get here twice of FC, and here it will be minus B to B FC. Similarly, when your SNF plus FC can be obtained by shifting the spectrum towards your left, so here we'll see it will be minus of twice FC, and here it will be having the band limited from B to minus B. So after adding, we'll get the SNIF is equals to SNQF, that is both are identical. So this power spectral density is same as that of the power spectral density of in phase component. Now here the area under the curve, that is integration minus infinity to infinity, SNIF DF is equals to twice of N naught B. Now we can see that it is similar to that of your power spectral density of in-phase and quadrature component. So from here we can conclude that when the mean of in-phase and quadrature component of narrowband process is equals to 0, then the power spectral density are identical, which gives the relation between in-phase and quadrature component with respect to power spectral density of narrowband noise process. So this was all about the narrowband noise process. In the next lecture, we'll discuss about the detection and estimation in digital communication system. Thank you.